Hello everyone and welcome to the Autodesk Robot Structural Analysis tutorial brought to you by the Civil Engineering Essentials channel. I hope you enjoy the video.
In this video, we're going to be talking about the slabs in Autodesk Robot, their design and design of reinforcement, and all the kinds of nice stuff that comes related to slabs. Now, before I start, this might be even a multi-part video depending on how long it takes. We need to understand basically the types of slabs we are faced with. There are like one-way beam and slab, there are two-way beam and slab, that is a flat slab with drop panels, and even a flat slab with column panels. And there is even two-way waffle slab with drops. So there are a lot of slabs involved. Now this might be a multi-parter, but I'll be talking now immediately at the flat slab. Some people call it the solid slab. Those are just namings, so I just showed you this because I want to refer to exactly this slab. There is a little technical detail I want to discuss very quickly before I start with this. Now, in some countries, they do basically differentiate between something called flat plate and something called flat slab. It depends on the country and the region you are in. Now, if you want to say, like for the same slab, some people call it flat slab, some people call it flat plate, some people call it solid slab, and it depends, to be honest, with the practice there. Even some people actually have like a solid slab with hidden beams. Now, there is no real classification I can go to because it depends on the region and on the design practice. For me, if you tell me a flat slab or a flat plate, I would understand a piece of concrete of a constant thickness, similar to this picture, resting on columns and being supported by 4 columns and having steel, just a steel mesh or I don't know, a wired mesh in both directions, top and bottom. That's what I would be understanding if you tell me flat slab or solid slab. In other countries, maybe they also include a beam inside it, but notice the beam is actually not dropped. The beam has the same thickness as the slab. It's not like this with a beam that is dropped. The beam has a thickness exactly as the slab, and the reason why they do beams is because they want to like focus the steel on the beam and stirrups in the beam. And if you have this kind of slab, if you have stirrups in the beam in this solid slab, then it has consequences in the punching shear. You see, if you do not have beams on the slab, then you have to check the slab for punching shear. If you do have beams in the slab, depends on the region, but personally I would think if you have beams that are in the slab, then beams should carry the shear and there is no punching shear because you are designing the stirrups in the beams, and basically the plate will not punch through except if you defeat the strength, the shear strength of those beams. So in this case you would design this for shear and for punching shear. This is similar to what you see in combined footings. You have a foundation like this and some people put a spine beam inverted on top of it. In that case, there is no punching shear check for the foundation, but you check the spine beam for shear. It's a long story. Maybe I will give you a foundation combined footing stuff later. I know I didn't touch on that. There is so many things I can talk about over it. This is really nice and really juicy. Also, at the time of recording, my YouTube channel has 998 subscribers. So I would like to thank each and every one of you. This was a real ride. I'm really happy about this. Now, what I will be discussing in this video is going to be a flat slab beamless. It's a long story, so let's get into it. Now, in this case, notice that those slabs, it's not just a 4-column slab. A slab like this would be big with a lot of columns here and there, but today, my point today is not to plan the structural system itself. There will be a video and I'm planning it. It takes a long time for planning, to plan how to start with architectural drawings and reach structural design. This takes a long time. The planning of this is something I will not be including. I will be assuming that my columns are 4 meters away. So, and I have like 4 rows of columns or 3 rows of columns. Let's see. I think I'm going to go for 4 with 4 meters. No, this is too much. So 3 meters. In the Y, I'm actually just doing the axis here. In the Y, I'm going to do this at 3.5 meters, so 3 repetitions, 3.5. In the Z, I have 0 and 3.5. Remember, my point here is to basically model a slab. So, well, I have this. Go to floors. I'll go and select me a thickness of Now, how much thickness do I need? I mean, I have 14. I have 4 meters. I think I would need 200 to 250 millimeters. I just say 200 millimeters now, and later we can check deflection. And the cool thing about softwares is that you can just change by a click and just reanalyze again. You can reduce the moment of inertia for slabs. Some codes actually require to reduce the moments of inertia of the slab. This accounts for the cracked section in concrete. You can even select a detailed reduction in the stiffness. And I'm just going to basically check me out on reference. I think this is from Bluebell, and I think they do mention this ASI flat slabs are 0.25 of I gross. So I'm just gonna go and reduce the inertia. 0.25 for everything. Parameters of foundation elasticity I do not have because it's not on the ground. I'll add that, I close that, and I'll draw it. But first of all, I need to grab me a shell here. I think I've changed the definitions. Did I change the definitions? No, because I think I tried something one day. So I just basically do me a very nice little cute contour. 1, 2, 3, and also remember that the first line you draw is your local x-axis, and this is required for the reading of the results. Fine. Now I'll just continue and add me some supports. I could add columns, but I want to add supports this time as nodes. So I'll just go to geometry, nodes. So I'm just adding me some nodes. Let's just make a final check. I click on the slab, double check here, everything is right. It's a shell. The section is, wait, why do I have ST100? Didn't I draw an ST200? Oh, I think I messed up. I think I didn't, yeah, it's good that I keep checking. I think I didn't select that, which is kind of strange. I added it, right? Ah, never mind, fine. I mean, I just can change it like this. Click here, slab thickness 200, and steel. What gives? I'm all over the place today. How come do I add steel here? Like, what's the, wait, it's like, that's kind of annoying. Did I actually add steel? Oh, huh. Okay, fine, I have to modify this. So I'll go to the thicknesses. I think that's a good way of seeing your error and basically double checking it. I have this tendency, professionally, I actually do double check everything. If I apply something like this, I check it very quickly here to make sure everything is nice. I see steel here. Can I modify it from here? No, right? Well, I can modify the thickness by double clicking here or going here to the thicknesses and double clicking this to modify to concrete. So I'll select the basic default concrete. So I just say CON and I get the concrete and I click on that. I'll add this, which will replace, and I close that and close everything. Now finally I just deselect, select again to double check if everything is right, and yes, it's concrete with its normal elastic modulus. I think we are good to go. Yeah, fine. So sorry, I'll go to the supports, I'll pin everything. Now this is an assumption that the connection between the column and the slab is a pin, which means that the column does not basically resist any rotation of the slab. It depends, of course, on your assumption and your detailing for that assumption. I think I mentioned this before, so I'll just ignore it. Now I'll go to dead load, I'll add me a dead load and add me a live load, and I'll just go to my dead load case. This is stuff you've seen millions of times. I'm assuming that you are well aware with the Autodesk Robot. If you don't, then I think I will link on top right side a video playlist that talks about the basics of Autodesk Robot. Alright, so I'll just go to the dead loads. I don't know, now we need, of course, the dead load calculation is something you'll learn in all your design courses. Let me just remind you very quickly. You have load partitions on the edges, you have wall partitions on the edges, wall partitions in the center, you have covering material both below and above, and this is something you learn in your elementary design courses in university. And I'll just be a little bit lazy here because my point is not to give a lecture today about loads. So I just go here and assume me like 900 kilograms per meter square of load, which is equivalent to -9 kilonewton per meter square. If you add that, I'll add this. This might be an overestimation. I just want to add this because my point here today is not to explain to you structures. Maybe in the project I will be doing for the full structure, I will be actually using Excel sheets to calculate stuff. Now to the live load, I'm gonna add me a load of, now it's between 250 to 400 kilograms. So By the way, the ASCE code does provide you with a live load that you should be applying to a structure. I just add me a 3.5 and I will leave the research, the research of the correct live load on you. I'll add that, close. Now in closing, I might go to loads, go to manual combination, add me an ultimate limit state, and basically say 1.2 dead, 1.6 live. Because I already have selected my correct codes, I can just do this and it magically applies you the factors. Fantastic. So far, this should be boring and should not be really something new. I mean, with the exception that you should check your stuff here, I don't think this is something new. If you run the analysis now, well, you get a finite element mesh. You get some errors, but they will be fixed soon. So if I go to MX6, I should see stripes. Well, yes, I do see them. If I go to MYY, I should see stripes in the opposite direction. If I go to shear, I should see high shears near the columns. This is stresses, my bad, shear forces. By the way, stresses is the axial stress, which is basically membrane forces divided by in the center of the slab. You can also change direction. We go to shear forces. I click on this, and I should see stripes. Yes, I do. They are also zigzaggy, exactly as they are supposed to be. For the lovers of finite element, if you go to no smoothing, you see an abomination. This abomination is totally okay and totally in the realm of what the finite element does. Actually, it doesn't look really as smooth as the softwares do try to show it to you, do try to sell it to you. So be my guest once again. You can double check Daryl L. Logan, first course in finite element. He talks about the smoothing process of the finite elements that you could get. I know this because I program my own software. Anyway, with that being said, I digress again. This is the second time I track. I have to backtrack again. I think my editor is going to be mad. So everything seems to be okay. Let me just check this. The deflections, yeah, maximum here. Okay, so everything seems to be fine. So you can see that you can double check those results from here. You can also check principal stresses. And I talked about the von Mises stresses before, I remember. So I leave it as is because I don't want to repeat stuff I've talked about before in this video series. Now I go basically to results, panel cuts. To just like playfully cut me a panel here, I'm trying to cut above the columns. I click the apply button. Now this gives you the moment around X, I guess, right? So to make sense, I'll go to maps and select moments around X to make sense of the cut. And well, you see those, basically those red places are tops of mountains and the blue places are basically bottoms of ridges or ravines or canyons. So it's kind of nice. Everything seems to be fine. Now I had a question about something called the wood&Amor results. I had a question from a dear subscriber talking about what the meaning of the calculation of reinforcements according to wood&Amor is. So of course there are multiple. Like there is NEN and there is wood&Amor. Now, I think I found an amazing article in LinkedIn that talks about it. This is really scientifically well. It's actually an instructor, Chinese, I guess. Anyway, it's one of those amazing instructors that talks about exactly why we need wood&Amor moments. You see, the moment XY is actually torsional twisting on the slab. Now, the torsional twisting on the slab does affect the bending on MX. It's not enough to calculate forces based on MXX alone, although it gives you a good indication. Autodesk Robot does do one extra step rather than just using this moment diagram. Truth to be said, I was using this moment diagram and adding me a factor of safety when I was a junior engineer, like back in 2010. But you know, getting more scientifically, the design of slabs is happening according to the wood&Amor principle. This is not a code. This is not a design code. The wood&Amor principle is just a principle that calculates the effective moments to be used in the design. And I'm not talking about complex stresses. I'm talking about the design now, which is the lower part. I think in one time I thought that this is also related to complex stresses, and I think I mentioned that. So it's kind of cool. You can read it, because you can see this 3D element and how the MXY actually affects MX and affects MY. You can see that the basic principle here is that you can't simply take mrx to add mx plus k mxy, and sometimes minus depending on the reinforcement. It's actually a k factor, and k is equals 1 is generally considered the best choice. I do not see, I mean, yeah, okay, fine, I see a reference here, but I mean, this is a good read, so at least you can check out what wood&Amor is. The only thing I want to say right now is that wood&Amor principle, it basically says that the x moment is the real x moment, is the x moment on the plate plus something about the torsion, because the torsion will affect both moments, x and y. And you can see this moment here happening in all cases. Of course, there is more reading to read about this. Now, how do you do that? It's not more circle, but based on the components of moments. You can actually find something called the principal moments, the maximum moments, because this mxy component will affect your mxx component and your myy component. So you can calculate a principal moment, I keep saying principal stress, which means that you would, in this corner, actually have perfect reinforcement to be perpendicular to your two moment directions, but this is not what we do. What we do is we just continue the mesh. So wood&Amor actually affects your moments, and you can double check this long read. It's kind of really cool. And even ETAPS does design based on wood&Amor technique. To say very quickly the following: mxx is not enough to design for the x, because this mxy, the torsion and twisting, will affect the moments mxx. So that's what wood&Amor is. And this is what is used in designing steel in reinforced concrete design of robot and ETAPS. So that's kind of cool. Now I will link the nice read here in the description of the video. It's really cool. I just want to reference our dear colleague. It's, oh my, that's a hard name. It's Chan Theun Chiv. I'm sorry, I'm not really good at pronouncing those names, so, but he needs to be mentioned because it's basically a nice read that he produced and it's worth reading. I'll link this into the description. Anyway, this is what Autodesk Robot does use for the design of reinforced concrete slabs automatically. I mean, so far so good. Now, well, let's go into the design. Now, what do you design when you use reinforced concrete design? Before we go to design, there is something about the mesh that I mentioned that I don't like. Quick update about the video editing. I'm pretty sure my video editor is now very angry. I tried play around a little bit with my mesh just to show you some stuff. It didn't work out, to be honest, because I tried to do it as fast as possible. I was unable because every time I wanted to do it, I thought, hey, you are winging it. So I just video edited almost 40 minutes of my recording time. Okay, so let's run the analysis again. I need a video that talks about meshing in the future. Yes, so I think we are ready to basically design that thing. So, well, I select my slab, go to design, or even better, I can select here and go to RC design and select slab required reinforcement. Now, if you click on slab required reinforcement, you are greeted with this GUI. Now, you can just do a dumb calculation to show you what happens. If you do just a calculation like this, which is not something I really, that's something I encourage, so to show you something very quickly here. If you do a quick calculation, then you can start seeing the areas and spacings and so on, the areas of the required reinforcement. Now, first things first, what happened when I clicked on calculate? If you click on calculate, notice that you have a list of panels selected. In this case, it's only one, which can be changed because you might have multiple panels, but you only have one. So, of course, you will only design this. The calculation for panel number is, well, the one. If you calculate, it starts filling. The limit stays used in this calculation are the ULS. You can see that it's case number 3. There is no SLS for the service load states, which means that, well, we forgot to do one. So how can I do one? Well, I can go to loads, and this is the beauty of robot. You can always catch yourself and improve. So I just go here, select this is an SLS case, serviceability limit state. I'll say OK, and check if it understands the one. Does it? That's cool. It added them as one-on-one. If you apply and close, you need to run the analysis again. You see, now I'm doing analysis stuff and I can recommit to the design when I finish. So okay, now of course my results are haywired here because they are no longer valid. But now you can do an SLS check based on the combination number. Oh, I think I should have named them, but okay, fine, there we go. Let's just calculate again, and well, let's see what happens. You have the results here, and to show you, now if you click on verification, you can verify stuff after the design. So if you click on calculate, you can now calculate a verification and no errors came out, which means that everything seems to be fine. You can actually verify the displacement using the combination tool. Displacement negative means displacement down, displacement positive means displacement up. You can verify them both if you want, but well, we usually verify the down displacement. I'll go back to calculation, repeat the calculation again just to make sure. While calculation, you have the ability to verify, by the way. It verifies automatically. Now, the results are read as follows. The required reinforcement can be X in the bottom, X in the top, Y in the bottom, and Y in the top. You also have something called spacing. Now, spacing needs you to select the bars. If you check this out, I think the spacing is strange. You have like 0 spacing, or for example, number of bars, how many bars you need. You can see the number of bars required. At least in this position, you need more bars in the X, which makes sense. And okay, so those are the required area steels. Now notice also that this is millimeter square per meter, so you can calculate the number of bars based on the assumption of steel. If you go to SLS, you can check out stiffness factors, deflections, and cracking. I go to reinforcement back and click on the A to see the area. Now this can be used to design, but Autodesk Robot is a really amazing designer himself. When it calculated the spacing between the bars, how did it do so? How did it know what kind of spacing to use and what kind of bars to use? There is something called the Slab Shell Reinforcement type. If you click on that, this is what you see when you had the shell defined. Now those are reinforcement definitions. You can use it to apply and to change things, but let me remind you that the reinforcement used on this was RC shell. Let me show you. If you go back to a structural model, to geometry, you can see that this is called RC shell, if I remember correctly. Let me select the shell. Okay, I think I'll... Okay, cancel first. There we go. I see this is ORC floor. Fine. I mean, I don't care what it's called, to be honest, because you can just define your own. If you go back to required reinforcement, back to this place, it was called RC floor. But of course, you can add your own reinforcement type. I will just show you what RC floor is. And I think we have a problem. Okay, let's hope it doesn't break down. I'm just canceling. Okay, it opened. Oh, I'm lucky. Now it's called RC floor, but of course you can change the name of it and you can add something new. The reinforcement calculations are based on bending alone, bending on compression, or compression and tension. You're saying RC floor, so obviously bending is dominant. But if you have an RC wall, let me show you without breaking robots. You see, an RC wall, robot automatically assumes that this is going to be a shear wall and you're going to design it according to compression and tension. Of course, you can define your own type and let robot design for both compression and tension and bending, which is basically a shell. So you can choose anything you want, to be honest. I just select the RC floor and modify it for now. I'm not going to modify it, I mean, I'm just going to show you. Now, the reinforcement direction is everywhere. I will leave it. You can make radial reinforcement. This is used if you have a circular, dome-ish shell. This happens in circular dome slabs, but I'll just leave it for you. The materials, well, it's as in the structural model, meaning he will use concrete that was defined here. You can select your material if you want to change it. I don't. Reinforcing steel is according to the ACI metric. It's grade 520, there is grade 420 and other grades. And for the serviceability limit state, if there is deflection, of course, and the allowable deflection here is below 30 millimeters, this is an assumption. You can actually go for long-term deflections. And this takes into account all the creep and stuff that you see. Creep being a real phenomenon, by the way. And finally, reinforcement. And this is where Robot calculated the spacing. You see, you have covers of 20 millimeters. That's small. I mean, I think it should be 25 millimeters, but I will leave it as 20 meters. You have diameters. You can see you have 4 diameters. Allow me to show you. I think it was diameter 10. Let's select, for the sake of arguments. Now 10 is okay-ish. For the sake of argument, I will select 522. Now this is an abomination. You don't select that big of bars in a small slab like this, but I'm just doing this for the sake of it. And I'll just add, and it doesn't want to change that. You can actually click on Note to have a quick rundown of all the stuff you have assumed. This is good for your report. Wait, I should have added this first. Okay, it doesn't even allow you to change anything here. This is kind of cool. It doesn't allow you to change anything because this is a default reinforcement parameter. Okay, fine, I'll do my own. So I'll say here, my own cool reinforcement. And I wanted to have everything. And material I'll use as the thing here. I will check deflection. I go to reinforcement and select 522s everywhere. Now this is ridiculous. Try 522 in a slab is, for a 20 millimeter slab, 200 millimeter slab is unheard of. I just add this, close, and now I will select this and click here and apply that. Now, oddly enough, I do not need to recalculate. This is strange for the structure, but I need to recalculate the reinforcement, right? So if I click on that, I'm expecting E to increase. Does it increase? No? Okay, I think, wait, the scale is all over the place. 850 millimeters, this is almost the maximum. I think it didn't increase because you have like 850 millimeters as your first spacing, which is kind of the maximum. So yeah, I think I owned myself. But you can see where this is going. You can select any reinforcement pattern you want. That's kind of cool. You can add your own reinforcement and double check whatever you want here. It's kind of nice. This, I think, should have changed some of my reinforcement area steel, right? Let me check something very quick. Area steel here, you get the maximum of, to see the maximum steel was around 1189. That's oddly specific. I think this is the minimum steel. I think Robot is designing for minimum steel, does it? Let's take a look. Reinforcement floor. Let's click here. Yes, and let's calculate again. Did I apply this? Wait, let me just double check again. Yeah, see, it changed. I think it changed. Let me see. Yes, 1131. And it is behaving exactly as I want. Fantastic. Now, are we finished? Of course not. There is punching here to be checked. There is drawings to be exported. So let's take a look on those. Now, since we calculated the required reinforcement, can we start providing reinforcement? Of course. You can go to provided reinforcement and you are greeted with this GUI. I hope my robot is not messing up. Okay, it didn't provide you with anything. I have a quick fix for this. You go to structure and model geometry. You select the plate that you already designed. And now you go to design, provided reinforcement for RC elements, and now it should automatically assume a slab. I hope it does. Yeah, there we go. I think we have it. It transferred the slab and the foundations. I don't want the foundations, I want the slab. So, because I defined supports. So it transferred the slab with its moments, basically, and its area still required. So, how can you start designing this? Now, of course, you can automatically calculate. So first things first, you can automatically calculate and everything seems to be fine. Now, before you click on the design or calculations, you have to quickly check out the calculation options. This is something I covered before. You can see once again the covers, but this time you cannot change anything in the covers. Wait a minute, why can't you change anything in the covers? Well, you see, you had the chance to change this accordingly, but now we have used a certain reinforcement model, so it uses this. If you go to concrete, it's fixed once again because it has implemented concrete. If you go to reinforcing bars, this is the selection of reinforcing bars that it will use. It uses grade 520. If you go to wire fabrics, you can switch from concrete bars to wire fabrics and vice versa. I will leave it. Reinforcement for punching shear. It might do this if it is needed, and I will show you later how you can check the punching shear. So well, it seems everything here is okay. If you go to this 1, 2, 3, which is the calculation options, I think, story parameters, sorry. You can just check if you have an environmental class and fire resistance. Now, I will not talk about fire resistance, but you can check out the time required for fire resistance, and it will try to meet it. Reinforcement patterns, I think. Now it's once again, I think I have a problem. Yeah, okay, there we go. For the reinforcement, you can select wire fabrics, which is basically this. You can select bars, or you can select wire fabrics and bars. Now, wire fabrics are something used in Germany. It's quite well known there. If you are like from part of the world which doesn't have wire fabric, you can go to bars and access that. It requires you to give its maximum length because it splices the bars if needed. I'll leave it for bars now. Now the bars, what it will calculate the diameters and spacings automatically. The spacing multiplier is 10 millimeters. That's kind of odd. I think 50 is better. The closest 5 centimeter for practical reasons. There is also preferred reinforcement spacing if you want. This warrants a deep dive for you alone. Just play around with those things and see how they affect your results. To put it quickly, bottom reinforcement, you can select the diameter to be a certain diameter from the selection. For the Y, the same thing. You can also click this button to, if you select 10, this will select 10 for top reinforcement, because you can have both. Sometimes we like to use like both settings for both layers. So this arrow basically does the job for you. I will go back to auto and get it back. You can take it back and forth. For the spacing in the direction, you can fix the spacing. I'm not a fan of that. I'm a fan of fixing the diameter and changing the spacing. So you can actually give spacings like at multipliers of 50, or you can give a list like 100, 50, 150. I'm more a fan of having a spacing multiplication. I don't have preferences. Maybe I want to have minimum spacing of 50, but it will do it anyway because I chose minimum spacing. I chose spacing multiplication. Wire fabrics reinforcement, you have some types where you can do your wire fabrics. I will leave it for you. Construction reinforcement, there is not much, but sometimes it adds you some hooks. And if you have like at the beam support, you can add a hook here. It's called bursting reinforcement in some parts of the world. It's called construction reinforcement, so those reinforcements are added for detailing reasons, and they are not included in the load carrying capacity. For the shapes, it is using a straight bar for the slab. You can hook it if you want, but I will leave it as is. So I think we're ready. I think it can calculate now. So let's calculate and even start drawing. So now it should give me a three-dimensional view. It doesn't. Okay, it went to final drawings. I don't want to go to final drawings. I want to see the reinforcement. So let's check. You can see that it applied for multiple zones, and each zone has its own phi. It seems that, yeah, it seems that it's trying to use the same phi with the same spacing, and it does have a slighter spacing in other zones, which is kind of cool. And it gives you a list of possible solutions with its kilograms, because if you select this, for example, it chooses different phis. Now this is why does it give you this solution? Like, look, you can select this solution phi 13 millimeters, but then you have two spacings. If you select this solution, for example, you still have two spacings. If you select this, you have only one spacing, 400. I am personally against having the spacing of 400. I am even against having a spacing more than the thickness of the slab. So I actually should have gone to the reinforcement patterns and asked it not to take a displacement more than 250. I'll just leave it without having any limitations, but I will just tell you my nuances here. This is why you need a human factor. Luckily for us, ChatGPT is not going to replace us humans in engineering. Editor, right? Yeah, anyway. I think this is still warranted because you have like double the spacing. Double the space. Now, practically speaking, I like this. I like this practically speaking because if you have a slab with double spacing, now the spacing is large, but my point being, if you have a slab with double spacing, then all you have to do is start having a gap. 1 bar yes, 1 bar no. 1 bar yes, 1 bar no. This is practical. Allow me to explain. Let's say that for the Y, you have not much reinforcement in the middle here. Let's say we are at the top Y now, okay? So you have small reinforcement near the center of the span and larger reinforcement above the places where you have higher moments in Y. If you have two spacings, one of them is exactly double the first one. This is good for practical reasons because then all you have to do is just to add a bar in the middle. This would cause you to have a half spacing. So having two spacings being exactly each of them half the other or double the other is practical for this reason. So I think this is a nice idea. Now, well, you get zones and you get top and bottom reinforcement. Well, this is, I can check it out here on the table. And, well, I think it makes more sense if you see the reinforcement. So, well, let's see the reinforcement. If you go to slab reinforcement, you see the reinforcement in detail. And you can see all those things where, I think this might be too much information. I think you can make it simpler. And this is why it's important to check out all possible. Look, I want to think loud here. In the end, you have skilled workers who are going to lay out the reinforcement for you. But it depends, of course, on the skill level of your workers. If you know or think that the team you have is 100% professional and they do know how to deal with multi regions like this, then be my guest and use this. If you somehow do not trust the workers you have, depending, of course, I mean, look, I don't know from where you're watching me, but not everywhere in the world you have those skilled workers who are able to read perfectly and do everything. Sometimes you have to give them instructions and be like on top of them. So if this multi-tier analysis and design is something a little bit too much, then you could basically just simplify it by choosing a different option. Of course, the bar here is calculated as 11.96. Why not 12? Our slab is 12, but you have 2 centimeters of cover on both sides. That's why it's 12.96. You see the 2 centimeter cover here. I think Robot is doing a great job here. Of course, you can go to the drawing now if you want to see it. And in the drawing, you have the slab. This is drawing 1 out of 4. I hope it works. If you click on this, you can see the slab reinforcement. This is the bottom slab reinforcement with its different regions, and each region has its own slab denotion, the annotator, and the top, which is a nightmare because you have multiple, and that's what I'm talking about, that I'm a little bit afraid on your workmanship because you have multiple regions, and I think this might be too tough of a call to be asked for. It depends on your workforce. By the way, there's a calculation note. You can check it out in case you want to see the calculation, how it was carried out. I will do a next video. This will be, because my video is almost 1 hour long, and it will be a nightmare to video edit. So I'll just keep this tabbed in your mind because I will be using this in reinforced concrete design. We'll be using the punching shear thing here for the first time, where you have the ability to basically use punching shear calculations to double check your work. This is something I still have not introduced in Robot, and this will be exactly the topic of the next video. So I'll stop for now, and I hope that this video was beneficial for you and that you enjoyed it. Of course, if you have enjoyed the video, then please like, share, comment, and subscribe, especially subscribing because it helps increase the reach of my channel. This is the Civil Engineering Essentials channel, and we'll catch you in the next video.